Good afternoon. My name is Karin Habshi, and I'm going to give you the CFD course. This is a very interesting course that has a lot of application in the engineering fields. So we will try to have a practical side by introducing you to a software as ANSYS Fluent that allows you to create a certain geometry, mesh it. When we say we mesh a geometry, this means we divide it into small parts, and then we can simulate, for example, let's say different HVAC configurations in a space. We can study the temperature distribution. We can study the velocity field, how particles, for example, can spread in a space. So this is one application of CFD. So it can be used for thermal comfort analysis. It can be used for indoor air quality study. So, for example, now with coronavirus, we try to reduce a lot contamination. So one application can be to study the spread of particles within a space. You can have heat transfer applications. Let's say you have a heat exchanger, you want to study its efficiency, how you can improve its design. All of this can be used using computational fluid dynamics. So the objective of this course is to introduce you first to the numerical techniques used in CFD on the theoretical level, and then also we'll have a practical side by uh, getting knowledge within a software, how we can use a software, how to interact with it. Sometimes also you can contribute to the modeling in this software. So you can write a small code and implement it to it. So this is more advanced stage. So you can do several things with computational fluid dynamics. So to start with, we'll go over the syllabus of the course. So the goal of this course is to teach the fundamental techniques used in CFD. CFD is computational fluid dynamics. It consists on numerically solving partial differential equations. You have already in fluids mechanics, you were introduced to Navier-Stokes relation, if you remember. These equations were very complex, and you come up with analytical solution for very specific cases. So if you remember, for example, you studied the flow in circular pipes. You obtained a certain analytical solution for laminar flows. And you have seen that for turbulent flows, things becomes much more complex. We need to use, for example, the Moody diagrams that can help us to solve these problems. And this can be much more complicated when you include the effect of turbulence, because the characteristic of when you have high Reynolds numbers, you go from laminar to turbulent regions. So you have what is called formation of eddies in your flow. You have a lot of turbulence in your flow, and this is very challenging to model. And this required a lot of research on this topic. And until now, we are still trying to find if it's possible to get analytical solution, and we still do not find solutions for this. So this is why we developed computational fluid dynamics, which is based on numerical solution. So it's not analytical, it's numerical. We'll see what is the difference between analytical. Analytical in general, it's an exact solution, while a numerical solution will give you an approximate solution. But when you develop your techniques, the error will be reduced and you can reach results very close to the reality. So in order to go to CFD, we should first understand the theory to establish the differential equations, as we did in fluid mechanics. Now, after we get these equations, we'll try to solve them in a relatively simpler way, because we didn't find mathematical analytical solutions that can give exactly, let's say, the velocity field if you have turbulence, if you have high turbulence levels. So to model turbulence, we come up with a lot of turbulence models, and we come up with numerical techniques that can lead to convergent solutions when we solve using computational fluid dynamics software. So we will begin with simple problems. So we'll consider, for example, first a heat conduction problem, how we can solve it numerically, how we can solve it analytically, and we'll compare solutions. And the course will discuss interaction of different heat processes as convection and conduction, leading to analysis of and the procedure used for fluid flow calculation. We will introduce several methods of numerical solution. So you have the finite difference technique, you have the finite volume technique, and we have the finite element methods that will be studied as different means of discretizing a range of equations that are required to solve problems in the engineering field. Now, concerning the delivery mode, so everything will be posted on e-learning. All PDFs and PowerPoints that we will use in the course material will be available. Plus, of course, recordings of online sessions, and hopefully when back on campus, we'll meet according to the schedule for the course delivery. Now, the work is distributed into 15 weeks. So we will start first with, within the first weeks, we'll have an introduction to the course. So first, we'll introduce what is CFD, what is computational fluid dynamics, and we'll give some engineering applications of CFD. Then, to be familiar with softwares that can be used, we'll introduce ANSYS Fluent. We'll see how we can create. So I will give you a certain problem and we'll use this problem to learn how to use a software. So we will create the geometry first, then we will mesh it. So we'll divide it into small control volumes. Then we will put the setup. When we say setup, this means we'll select the appropriate algorithms to be used. We'll select the numerical methods that we want to use to solve our problem. And of course, the theoretical part will help you to understand these algorithms, how they work, how we select them depending on the application. So this will require a certain experience so that you will gain with this course. In week 3, we will review mass and momentum conservation and Navier-Stokes equation. It's very important to understand these relations because when you use Fluent is a closed box. So you give it boundary conditions, you give it your geometry, and it will, after you specify the algorithms it will use, you don't know how calculations will take place. So you just run calculations and you will observe results. So if you don't understand well your equations, you will not be able to play with the parameters in ANSYS to have a convergent solution. So when you understand well the physics, if you have divergence, you can come up with several solutions to reach convergence. So with practice also, you will have some expertise into what are the main reasons that can cause divergence. How can I reduce them? For example, I can reduce the mesh size. I can, if I have a transient application, I can reduce the time step, etc. After this, we'll do also a review on kinematic properties of fluids and dynamic similarity and energy conservation. In fluid mechanics, in the last chapters, you introduced similarity. And this is a very important idea when you use CFD, because sometimes, let's say you have a very big scale. And let's say you want to study an airplane or you want to study a very large scale building. You can create a certain model if you want that is much smaller in size, but if you satisfy similarity conditions, you can extrapolate your result. So this means with a smaller number of elements, you can reach conclusions that can be generalized through dimensionless groups and that can be used to the real case as application for the real case. So it's very important to know what are the conditions that will give you similar, if you want, model and prototype. So they should have same dimensionless number. If you remember, one of these are Reynolds number, drag coefficient, lift coefficient, etc. So we'll do a small review on these dimensionless numbers that are very important when we want to do the analysis of any engineering problem. Now, one key for good results in CFD is to appropriately input the initial and boundary conditions, because the solution will depend on these conditions. So if these conditions are not set in a good way, it will give misleading results. So we should know what are the different types of boundary conditions, how to select them, how to input them, etc. In addition, as we discussed now, one of the main challenging fields is turbulence, flow turbulence. And flow turbulence required a lot of research and required a lot of scientific work to model it. And so I will introduce you to the main models used for turbulence. What are the variables implemented, and what are the equation governing these turbulence variables, and which model to use depending on the applications that we have. So we'll see together that there is a lot of turbulence models. We start from one model equation, so we just add one variable. You can go up to adding 7 variables and more to solve for turbulence. You have a variety of models that can be used. We'll see from the simplest one to the more complex one. Now, we'll also do some applications. So in CFD, we will take several turbulence examples and see, we can compare. Sometimes you can do it by trial and error. So you can, let's say you have some experiments performed in a wind tunnel, and you want to check for this application, which model is the best. So you can use CFD, you can run your simulations with different turbulence models, and you will select the one which will give you the closest result to your experimental results. So this is what we call model validation. So whenever we develop a CFD model, to make sure that it's working appropriately, we can compare with previous data from literature, or also we can compare with experimental results. So we can build a geometry that is similar to the one studied in CFD, and then we get results from CFD, we get results from experiments, and we compare. And in this way, we can tune our CFD model in order to get exact or results that are in good agreement with the experimental or literature results. In this way, we can, with experience, know that for this application, this model works the best. For another application, it's better to use another model, etc. Also, we'll learn discretization techniques. So discretization is very important because it will help us to go from an analytical equation to a numerical one. So for example, any derivative, if I take the simplest derivative, let's say the derivative of position with time, dx by dt. This is an analytical form of the derivative. If I want to transform it into, if I want to calculate the derivative in a numerical way without knowing the exact function. So if you know x function of time, of course, the easiest thing to do will be to use the mathematical tools and to derive this function with respect to time. But if you don't know this function and you want to solve for it, then you can model dx by dt as delta x over delta t. And the smaller the time step you take, the closer you will be to the actual derivative. So by reducing the time step a lot, you can numerically be very close to the actual derivative. So discretization will rely on this. So we will transform equations from differential form to numerical form. Okay. Now we'll apply a discretization technique on the diffusion equation, and we will learn techniques that can be used to facilitate the solution of discretized algebraic relations. So one of them is the three-diagonal matrix algorithm, which is an algorithm widely used in numerical techniques. We'll also introduce, as we said, several methods to solve numerically. So one of them is the finite volume method that will be introduced to solve convection diffusion equations. We'll also learn algorithms used to couple pressure and velocity. So we'll see together that pressure and velocity variables are dependent on each other. And we will learn some numerical algorithms that allows us to couple these variables. Another idea that we will tackle is the finite volume method for unsteady flows. So we have some applications, some steady applications where the time variable is not involved. So we don't have variation with time. And we have other applications that are transient or unsteady. So in these cases, we have specific treatment for the transient terms. So we will see how to use the finite volume method for the case of unsteady flows. Now, as we previously said, boundary conditions are of high importance into getting a good solution. So if you give bad boundary condition, you can expect bad results. So we will see what are the errors that can be involved and how to select the appropriate boundary conditions. Also, we will develop methods to deal with complex geometry. So we can see, for example, that if we want to mesh a simple domain, if we have a rectangular domain and we don't have a lot of curves, and you have objects in this domain that are all of straight sides, you have cubes or just rectangular parts, you can use a grid that is orthogonal grids. So your elements will be cubes or you can have rectangular elements. However, whenever you have curves in your domain, so let's say you want to simulate a human body. The human body includes a lot of curves. So if you want to mesh it, you cannot use rectangular elements. So you need to use, for example, triangular faces, and what is this in 3D we call them tetrahedral elements. So we will learn how to mesh complex geometries. And of course, for this course, we'll have exams and we will have projects also. Okay. So now concerning the grade distribution, we'll see it together. So the grade is divided into 10% of attendance and participation. You have 2 tests on 50%. We can, if you want, we can modify this. We can include a project. So we do 1 midterm and 1 final because we have a practical side of this course. So we can replace one of the tests by a project. Then we have a midterm and a final. Concerning the textbooks, as I told you, all lectures will be provided for you on e-learning, but in case you wish to have extra readings, these are references used in this course. So you have computational fluid dynamics, a practical approach. You can easily download it from the internet. And you have also an introduction to computational fluid dynamics, the finite volume method. So this is the syllabus of the course. I will start with you with a brief introduction on CFD.
دكتور سوري أنا فوت مؤخر على الصف بخصوص البريزنسيال عندك كتير حضوري ولا كيف؟
هلا it depends on the regulation of the university. هلا they said until February 15 it's online. هلا we will discuss this. If you find the online mode efficient and you prefer to continue with it, I don't mind, as long as it's fine for all. Okay.
والexams بريزنسيال أكيد.
أكيد. Exams should be on campus.
Thank you.
Okay. So let us start.
Can we do one project and one final exam?
In general, it's recommended to have 2 exams. It's even better for you for a better distribution of grades. Okay, because just sometimes if you don't do well in the exam and then you will have a very high percentage on it, it's bad. So at least you should have 3 grades. Let's say 1 project, 1 midterm, 1 final. Okay.
Okay.
Yeah, just 1 second, it's opening. Okay. So in this session, we will introduce CFD basis and the use of ANSYS Fluent in engineering application. To start with, fluid dynamics is both interesting and challenging field for study and research. In real world, almost everywhere fluid is present. So we need fluid dynamics to describe or model these fluid flows. Now, whenever you have a certain fluid flow problem, to solve it, you need to write first the basic physical laws, which are the continuity equation, which deals with mass conservation, the momentum equation, and in case you have, let's say, constant viscosity, they are called, and constant density, you call them Navier-Stokes equations. And they are based on writing the Newton law, the Newton second law for a certain control volume. And the third relation is energy equation, conservation of energy. So you write the balance of energy for your control volume. Okay. So always, whenever I have a fluid problem and I want to solve it on the micro scale. So since if I want to find the temperature at every point of the space, so I need to do a micro scale analysis. I want to take a small control volume. I want to apply on it the different conservation equations. So what is the idea? The idea is to take a small element. Let's say first I apply mass conservation. I consider all fluxes of mass that can come in and all fluxes that can go out, and I apply the conservation of mass. I will remind you how we derive all of these relations after in the review of conservation equations. But the idea is just to consider a certain control volume and to apply on it conservation of mass to get continuity. So I will consider all possible fluxes getting in and coming out. I do the balance that any storage, okay, any storage of mass plus summation of mass flow rates getting out minus summation of mass flow rates going in is equal to 0. This is the idea. Now, in case I have, for example, a steady application, then the transient term will cancel out and I will end up with sum of m dot in equals to summation of m dot out. So everything coming in at the end will go out, because for steady application, I don't have accumulation of mass. So because if I have accumulation, this will lead to a transient state. So the mass within my control volume will change with time. If I have steady state cases, this means the quantities that will come in should go out. Okay. So by writing the balance of fluxes of mass, I can write the conservation of mass for this control volume. I can now move to applying a Newton law on this element. So I will have to consider all possible forces acting on it. And after I do this, as I told you, we will go back again to the theory of these equations in detail. But after I write Newton law for this control volume, I can project these Newton laws. You know that it's based on sum of forces equal ma, and this is a vectorial relation. I can decompose it into 3 directions. If I'm working in Cartesian coordinates, I will decompose it into x, y, and z. This give what is known as Navier-Stokes equations in Cartesian coordinates. And the conditions for Navier-Stokes is to have constant viscosity and constant density. So if these are not constant, this will also complicate the analysis and will require developed numerical techniques to solve for these equations. So if we do a small analysis of the terms, since we are doing sum of forces, so from one side we'll have different forces acting on the particle. Now, since we simplified by the mass, you can get forces per unit mass. So for example, these terms will represent the gravity force per unit mass because it's related to G. You know that the weight is m times g. After simplifying m, you still have the component of g into x, y, and z. You have the pressure forces. So pressure force, gradient forces per unit mass are represented by these terms. And you have viscous effects. So viscosity is the tendency of a fluid to oppose the relative motion between fluid particles. So viscous forces will also affect the fluid behavior, and these terms will account for these viscous forces per unit mass of fluid. And as expected, since it's based on Newton's law, sum of forces equal ma. So after simplifying m, you should have from this side an acceleration term. And in fluids, you have seen that your total acceleration can be decomposed into a local acceleration and a convective acceleration. So what do we mean by this? We mean that if I observe a certain point in space, okay, if the variable is varying at this point with time, we call it local acceleration. If the property is varying with space, so this means if my particle is moving from location 1 to location 2, it's experiencing different velocity. This is acceleration with space, which we call convection acceleration. So the total acceleration will be the combination of local and convective acceleration. So these are the Navier-Stokes relations. Now, these equations were very challenging to solve, and they consist of nonlinear partial differential equations, and we were not able to find a general closed form solution. And even it was one of the main mathematical challenges, and we offered very high prizes for people that can solve them, but no one was able to find an analytical general solution for these equations. So closed form solutions were only possible for certain simplified problems. For example, in fluids, you have seen how to find the analytical solution for a flow within a pipe, for example, or also, let's say, if you have flow over a flat plate, how the flow will behave. So these simple problems, but for more complex scenarios, if you have, for example, flow over a car or flow over an airplane, you don't have an analytical solution for this. You should find the solution numerically. So for complex problems, computational fluid dynamics, CFD techniques should be used. In order to solve, we need to supply the geometry. We need to write the boundary conditions for the solution domain where the fluid is contained. We need to write the initial conditions if the flow is unsteady, as we already said. And we will try to simplify the equations as much as possible. So sometimes, let's say, if you have a certain problem where radiation effect is not very important, no need to model radiation. So you just say, I will enable the normal energy equations, including conduction, convection, etc., without taking into consideration radiation. So it depends on your problem. You should try to simplify as much as possible, because more you do simplifications, you can reach in a faster way the solution. Of course, these simplifications should be justified. So for example, we can say that within a space, to neglect radiation effects, you should not have large gradient in temperature within the space, because large gradient in temperature between your surfaces will lead to significant radiation effects. So always these simplifications should be justified. Now, once you simplify your problem, you select the models that you will use, the energy models, the turbulence models. So you can start to perform, if you want to try analytical method, if you were able to simplify to a large extent, you can try to integrate analytically and to find the solution. And if not, if the problem is still complex, you can go to numerical techniques. And you should apply appropriate initial and boundary conditions to solve your problem and to get your constant of integrations. Now, so as we said, some problems can be simplified so that we can get a certain analytical solution for them, while other problems are challenging. Like, for example, if I want to simulate the flow over a car, if I want to study the curvature of a spoiler, or what should be the curvature of the car to reduce drag as much as possible, etc. So, for example, here you can see the simulation of a BMW car using computational fluid dynamics. You can observe the velocity field around the car. You can observe the pressure field on it to know, for example, what are the mechanical constraints for which are subjected this car, what is the appropriate material to use to avoid any possible failure, etc. So CFD is very important for engineering design. Now, we have three common ways to solve engineering problems. The first one is the analytical or theoretical approach. So we will develop first, as we said, these equations. So we will go back to fluid mechanics, to heat transfer, to write our analytical equations, and we'll see if there is possibility to solve theoretically. So for certain simplified problem, as we said, there is an analytical solution, but for complex one, there is no analytical solution. So we should think about other techniques to solve them. So the analytical theoretical approach will use laws and theories and associated equations such as Newton's law, continuity, conservation of energy, and will solve analytically these solutions to get, let's say, the temperature, the velocity, field, etc. And these solutions will be exact solution. So the advantage of analytical solution is that they provide exact solution. But what is the challenge? That for several engineering problems, we're not able to reach analytical solution. So we should think then about other methods. Now, other methods includes or experimental work. So I need to perform experiments and try to understand the different physics affecting my system and relate the different variables. For example, let's say wind tunnel experiments are widely used. They will help us into the design and optimization of shapes of airplanes, ships, automobiles. So we know that, for example, if you want to, let's say, design an airplane, you can construct a small model of an airplane and test it in a wind tunnel. So you can perform a lot of experiments to understand the physics behind your problem and come up with suggestions to improve your design. Now, what is a little bit challenging in experiments is that they take a lot of time. They require also high costs sometimes. So it's not always practical to rely only on experiments. Experiments can be good, can be a support for design, but we should rely also on other tools that are faster and will cost less. This is then the cause why we go to numerical approach, or which is computational fluid dynamics. So in the numerical approach, we will try to solve a fluid problem using numerical techniques. Now, the good thing about this approach is that we save time and we save cost, but the problem is that these methods are approximate and not exact. And our purpose in this course is to try to reduce the error of these techniques and develop several numerical techniques that can be used to solve complex engineering problems. Okay, so this is a brief introduction to this course. We'll continue with explaining what is CFD and why we use it and what is its main application next time. Thank you for your time. Any questions?
Merci, doctor.
Welcome.
Merci, doctor.
Okay, so we meet next time, hopefully at 5:50. Bye.
Thank you.
Thank you, doctor.
Bye.
Bye.
Thank you,
Bye.
doctor. Bye.